Hello everybody! I hope you're having a wonderful day. So we're going to be proving another property of big O today. We're going to be proving the transitivity of big O. Now, transitivity is one of these properties that I mentioned, like reflexive. So again, I'm not going to go into too much detail about what relations are here. We may at some point. But the big point here I want you to take about what transitivity is, and I'll give you an example of what I mean, is if F is big O of G and G is big O of H, then you can imply that implies that F is big O of H. So do you see how if you read this, you start with F, then you talked about G, then G talks about H, you cut out G from the middle and you can now talk about F in relation to H. Transitivity allows me to make these very simple jumps between these different sets of complexity functions, as long as I have a so-called middleman. So that means that I could make, so if I know as a given that n is big O of n to the power of k, and I already know that n to the power, I know any polynomial is big O of 2 to the power of n, I can make this immediate jump. And this is because of transitivity. So this is not a property you should take lightly. It's a nice shortcut. So if you know that big O is transitive, you can make these kind of jumps. So this is a pretty handy thing to know and be aware of. So what do? We find constants. C, remember C is a positive real number. And n0 is a positive integer, right? Where f of n is less than or equal to c times h of n for all n greater or equal to n0. So now I'm going to invoke a very similar pattern to what I did before, and you'll see quite quickly how this becomes very handy. So the big thing I want you to take note of is that I know that f is big O of g, and I know that g is big O of h. So we're going to use that in my proof, or our proof, I should be more precise, to prove the general claim. So we're going to use some of the techniques that we've seen previously to prove this claim. Since f is big O of g, and g is big O of h, what does that mean? That means that there exist constants, right? I'm going to write it in this compact way. Makes it a little easier for me to write everything down. There exists constants. C1, C2, which they're going to be positive real numbers, and N1 and N2, which are positive integers. Such that both, and I'm just going to write down what each one of the inequalities would be for each one of these two invocations of the big O definition. Remember, I've used it twice. Once for this one, once for that one. That's what each of these pairs of constants is for. Such that both f of n is less or equal to c1 times g of n. And this is, of course, true for all n greater or equal to n1. And g of n is less or equal to c2 times, is it g or is it h? It's h. Don't get too hung up too quickly. Got to make sure you write the thing down carefully. Got to make sure we write our things down carefully. So we have f is less or equal to c1 times g of n for all n greater or equal to n1. And g of n is less or equal to c2 times h of n for all n greater or equal to n2. I'm going to use the same strategy I did last time. Notice that both these inequalities would be true anyways if I picked the larger of these two constants, n1 and n2, right? So I'm going to use that. So I'm going to choose. So this is going to be one of the few times you're going to see me pick n0 first. So this is pretty handy if you just realize this. It's a matter of finesse. You'll notice that some ways I write things, you'll notice that there's a little bit of finesse to the way I write things down. So, for example, there's sometimes where I maybe won't pick n0 right away. I'll instead write down, for example, that, oh, well, for all n greater or equal to the maximum of these two things, then I get the inequality that follows from summing these two inequalities. Just as an example. I'm just going to do it here just because I feel like changing it up a little bit so you can see some variety. So I'm going to make n0 be the max of n1 and n2. Then we find constant. We need to find constant c so that f of n is less than or equal to c times h of n for all n greater or equal to n0. So now I'm just going to use these two inequalities here like I did when I was actually proving another property of big O previously. Using the above inequalities, now if it's unclear what you mean by above, you may number these two inequalities and say by inequality 1 and 2 or A and B, if you call them 1 and 2 and A and B respectively. Observe that for all n greater or equal to n0, we have the following. Now what I'm going to do is I'm not going to sum over them this time. Instead, what I'm going to do is I'm going to try to compose these in a way such that I eliminate G right here. So I want to eliminate the middleman. Like I said, that's going to be the idea here. And it's going to pop up in our proof as well. So what I'm going to do is I'm going to write, so I know f of n is less than or equal to c1 times g of n. We actually used this strategy at one point for another example that you may have seen in the past that I've done. There's no coincidence to that fact. This is just another one of these cases where these general properties actually provide a skeleton for another type of proof that we may have. So if you know, say for example, big O is transitive, you might be able to find that, yeah, no, there's no coincidence to how I'm arguing this. It's actually just a feature of big O. So f of n is less than or equal to c1 times g of n. Now we know that this is less than or equal to, so what's g of n less than or equal to? c2 times h of n, right? So I'm going to have c1 times c2 times h of n, right? So I replace g of n with this because that's what's sitting right here, right? And we made sure n was big enough. Now what do? I'm going to rearrange these terms a little bit. I'm going to put c1 and c2 together as a product. So I have c1 times c2 times h of n. What should I pick for c? What should c be? So remember, f's all the way over there. F of n is less than or equal to c1 times c2 times h of n. So what should c be? Well, it better be the product of these two, at least, right? So let's pick those two. So let's pick c to be that. Select c is to be c1 times c2. Therefore, by the definition of big O, f of n is, f is big O of h. And we're done. Piece of cake, right? So notice all I've done here is I've written out what the definition of big O is. That's all I did. I wrote it out, I invoked it, and then what I did is I used a little bit of clever thinking to combine them in a way such that I can go from f to something in terms of h. And by doing that, I expose constants in a way that if I argue in carefully, like this, I can get c and n0 really nice and straightforward fashion like this. Like I said, we've proven claims that use a structure very similar to this. In particular, an example of this would be when I talked about B-smoothness. The proof that I gave for B-smoothness actually uses the transitivity of big O. In fact, if you look at my notes, I give an example of how you'd use transitivity for for proving B smoothness, which that was a part of the smoothness section of our lessons. So you can find all sorts of places where transitivity is very helpful, but like I said, it's a nice, easy way to eliminate that darn middleman there. So if you can get rid of the middleman, if you know something about that middleman and it connects to H, if you know what's going on between the one you're interested in relation to the middleman, you can get rid of the middleman and go right to the real claim you want to prove. Okay, so that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.